Hey guys, so last time we talked about the binomial formula, how to apply that. We did a lot of practice problems to make sure that we understood how to use it. So now let's go ahead and move on to the binomial table, which is basically a simpler way for us to do all this math. So once you have to calculate 3 or more binomial probabilities by hand, things can easily just get nuts, right? So we have the probability of x is less than 3. So the number of successes is less than 3. That would basically have us calculating 3 binomial probabilities. Each of those takes a lot of time to do, probably a couple minutes each. So it takes us a while to calculate something, for example, like probability that the number of successes is less than 3. The good thing is that the book has the binomial table. Let me go ahead and put this in red. Has a binomial table to take care of this nightmare. And so below is a sample of the table. And so before we get into that top formula up there, let's go ahead and just talk about what this number that I highlighted right here represents. So this table has cumulative probabilities. So it's probabilities that aren't just of this particular instance of successes, right? So even though I looked up, if you go across, you look up 3, that 3, this probability here, it doesn't represent the probability of exactly 3 successes. This is the probability of at most 3 successes out of 5 with a 77% chance of success. So we have 3, but it also includes all the ones below it. And again, this is our number of successes. N is what again? It's the number of trials, right? So we do this experiment so many times, we find out how many successes we're interested in. And then also, here P, this is the probability of success. So this should all be kind of a review in terms of vocabulary, but again, this table is something new that we haven't seen yet. So another way of saying this is that 0.472 is the probability that the number of successes is less than or equal to 3. Or again, at most 3 successes, right? And so probability x is 0 plus the probability x is 1 plus the probability x is 2 plus the probability x is 3. That's how this table works. And so that's why this formula up here looks very, very complicated, but essentially all it says is this formula tells you the probability for the number of successes to be less than or equal to a particular number, aka the probability that x is 0, 1, 2, 3, all the way up to the number of successes that we're interested in, right? And then below here I basically tell you that essentially each of those probabilities is its own binomial probability. So here we have a combination. So combination for 0 successes. The combination and binomial probability for 1 success, 2 success, 3 successes, 4 successes. So technically, if you have to do this by hand, you would have to do a bunch of these back to back, and that would be really annoying. So that's what's good about the table. It kind of gives us a shortcut, and it gives us a probability, a cumulative probability. So since it gives us cumulative probability, we have to do a little math and thinking whenever we do a problem. So let's go ahead and dive on into some examples. So in a game of slots, the chance of you winning any money is 30%, including small wins and jackpots. What is the probability that if you win all the money, if you win money, and at most 3 out of the 5 game slots? So we have 5 game slots, so what does that 5 represent? That means our N is 5. How many successes am I interested in? At most 3, right? So I want at most 3, aka 3 or anything less, right? Now what's my probability of success? Winning money is 30%, so 0.3. And failure is 0.7, right? So again, we're just going to write all of our pieces of information so that we don't have to refer to the problem anymore. It saves us some time. So now, we want the probability that x is less than or equal to 3. So how do we get that from this table? Well, basically, first things first, you have to find the n. And again, this is just a little kind of excerpt of the table. The full table is at the end of all these packets. So after the last concept, you're going to see also the binomial table fully ready to go. So the probability that x is less than or equal to 3. We go up to our table, we find the number of trials that we're interested in, right? Because it's broken down by n equals 5, 6, 10, 12, things like that. So this is the set for 5 total successes. But now it has a bunch of probabilities as well. So we're going to have to go to the probability of success of 0.3. So we'll go to 0.3, right? Our n is 5, so that's good to go. And then how many successes are we interested? 3 or less, right? So if we look up 3, we get 0.969. But is that the probability that we're interested in? Remember, 0.969, this table adds up everything before it, right? So that actually is the probability that we're interested in, because what it's basically telling us is 0.969 is the probability of 0 successes, which was 0.168, plus 1 success, plus 2 successes, and plus a third success, right? So it includes all of these probabilities that we're interested in. Probability that's 0, plus probability that's 1, plus probability that it's 2, plus probability that it's 3. That's all equal to 0.969. So we see very easily that this table can help us a lot. So instead of having to calculate 4 of them, we can go ahead and just get it from the table and find that it's 0.969. That makes sense? So again, x is less than or equal to 3. You literally will just look up that number, and that's the probability that you're focusing on. But now let's try a couple of different alternative versions of this question. So referring back to example 1, what's the probability that you will win money in at least 2 out of 5 games of slots? So again, let's go ahead and write our information. So n is 5. Our probability of success doesn't change, and therefore our probability of failure is still exactly the same, right? But our number of successes that we're interested in is different this time. This time we're looking at what's the probability that there's at least 2 out of 5 games won, right? So at least 2, that's 2 or more, right? So we want greater than or equal to 2. So this is a little different than the one before where we said at most 3, right? At most and at least are kind of like complete opposites. So the probability that x is greater than or equal to 2 equals the probability that it's 2 plus the probability it's 3 plus 4 plus winning all 5 games, right? So that's all the probabilities that we're looking for. Again, we don't want to calculate it, so let's see if we can find kind of like a smart way for us to find this probability. So 2 or more. So once we look this up, we see that 2 or more is essentially, let me go ahead and put this in a different color. We're still at n equals 5, p equals 0.3, right? But we look up 2, and that gives us 0.837. But that probability is for 2 or less, right? So since everything is very much this number or less, finding a number that it's this number and greater is a little weird. And the reason for that is because we have to use complements now. So probability that x is greater than or equal to 2 is the same thing as 1 minus the probability that, what's the opposite of x being greater than or equal to 2? It's just less than 2, right? So probability that x is less than 2. But our table only works off of less than or equal to, right? So what numbers are less than 2? Right, so we're basically just transforming that less than 2 into a less than or equal to some number. So less than 2 wins, we have 1 or 0, right? So another way of writing the probability that x is less than 2 is x is less than or equal to 1. Now we're good. So see this special kind of number here, this little variable or function, less than or equal to, is very important. And that's the one that our table works off of. So we always want to write our formulas in a way that we get less than or equal to. So we got less than or equal to 1. So let's go ahead and look that up. So less than or equal to 1 gives us 0.528. So 1 minus 0.528, and that gives us 0.472. Crazy, right? So let's just recap that again. So we wanted the probability of at least 2 out of 5 games won, so that's 2 or more, right? But our probability table, our binomial table with all the probabilities, doesn't work off of 2 or more. It works off of 2 or less, or a number of successes and less, any given number. So what we do is use a complement, but the complement for at least 2 games being won is less than 2 games being won. But again, our table doesn't work off of just less than. It works off of less than or equal to. So the number before the 2 that would fall into that less than or equal to kind of situation would be 1. So the probability that x is less than or equal to 1 is the same thing as saying the probability that x is less than 2, right? Because less than 2 doesn't include the 2, and it just includes 0 and 1. So now that we have our function in terms of a less than or equal to type of statement, we look up that number itself, the number of successes that we're interested in, and then 1 minus that gives us the complement, right? And so let me go ahead and write down, essentially, this is what's happening, right? We have greater than or equal to 2, greater than or equal to 2 on this side, and then less than or equal to 1 on the left side. Does that make sense? So that's why we do greater than or equal to 2. Cool story, but that's not where my table works off of. So let's use a number and down. And so the best one would have been 1. Cool? So let's try out one more. What's the probability that you'll win exactly 4 out of 5 games of slots? So n equals 5. X, we want exactly 4 games won, right? Probability of success is still 30%. Probability of failure is still 70%. So, probability that X is exactly 4. Now, this one's a little more complicated to think about. So, 0, 1, 2, 3, 4, 5, right? And then let me do it one more time and I'll show you why. So, essentially, we can look up 4, but 4 would get, let me go ahead and remove myself actually. So, 4 would give us 4 and less, right? Does that make sense? But is that what we want? We don't want 4 or less. What do we want? We want exactly 4, right? So what we have to do is a little math. So here, X is less than or equal to 4, cool story, but if we do another one, this one is X is less than or equal to 3, right? So if we look up 3, we get 3 and down. So essentially, if I subtract these two probabilities, what am I left with? If I subtract the probability that X is less than or equal to 4 and X is less than or equal to 3, what's left in between these two is exactly 4, right? Because for the top one, I don't include 5, I just include 4 and down. And on the bottom one, I don't include 4, so I have 3 and down. So basically, by subtracting the probability that X is less than 3, I get to mathematically just remove all of this stuff, right? So when I subtract it, I basically removed probability of 0, 1, 2, and 3 from the probability of 0, 1, 2, 3, and 4 when we said the probability that X is less than or equal to 4. Does that make sense? So let's go ahead and look up on our table. This ends up being X is less than or equal to 4 minus the probability that X is less than or equal to 3. So once we look this up in our table, do not go this way. So here I am back again. Once we look this up on our table, when we look at 4, we get 0.998, and 3 gives us 969. So 0.998 minus 0.969, and so we end up with 0.029. Cool? So there's some applications of the binomial table. It's once you get it down packed, it's actually very easy to use binomial table. So I have quite a few practice problems in the next section just for us to go ahead and try this out and apply this over and over again. So that's about it. Let's go ahead and move on to the practice problems.